Alright, I'm Daniel, welcome back. Like I promised in this video, we're going to start seeing collections in practice starting with sequences. Cool, so let's create a new application in the Part 3 functional programming package, and let's call this sequences. Make this an object, of course, and at the end extends app. So we're now ready, and the first thing that I want to talk is about sequences, which is denoted by the type seq. So sequences are a very general interface for data structures that have two properties that have a well-defined order, and they can be indexed. Sequences have a lot of operations supported out of the box. For example, indexing and iterating. The apply, length, and reverse methods are particularly used. We have concatenation and appending and prepending to construct new collections, and we have a lot of others. Besides map, flat map, and filter, we have grouping, sorting, searching, slicing, and all that kind of stuff. So let's see it in practice in the IDE. So if I construct a sequence, and on the right hand side I used the apply method from the seek companion object, and I put in a 1, 2, 3, 4 like we did with list. Then if I print line a sequence, then I should see the sequence 1, 2, 3, 4 with a little twist that this sequence is actually a list. So the seek companion object actually has an apply factory method that can construct subclasses of sequence. But the declared type of a sequence is sequence of int. Now let's use some of those utility methods. For example, a sequence dot reverse will get the list 4, 3, 2, 1. If we have, for example, a sequence dot apply with the number 2, then that means a sequence dot get basically at index number 2. So we should see the value 3 here. So the apply method retrieves the value at this particular index. Let's use some other methods. For example, if I try to do a sequence plus plus, which is the concatenation, and put in another sequence, let's say 5, 6, 7, then I should be seeing the list 1, 2, 3, 4, 5, 6, 7 here in the console. So this plus plus operator is actually very handy. Also, some sort methods are often used in practice. Sorted, especially if sequences are tagged with the type, which is a numerical type, or something that's comparable. The sorted method works out of the box. So if let's say I have 765 or 756, just to break the ordering. Oh, I see the list 1, 2, 3, 4. Let's break the ordering here. If I say 1, 3, 2, 4 or something like that, just to see how the sorted method actually works, right? The sorted method works if the type is by default ordered. Now, how this magic actually happens, we're going to discuss in the advanced Scala course. And before we move on to lists, I want to talk about ranges, which are also sequences. So if I say val arrange, which is a seek of int, and on the right hand side I put in, watch what I'm writing, 1 space 2 space 10. So 1 to 10 is a collection, which is a range, and this can be a sequence here. So if I put in a range dot for each print line, then this will print all the numbers 1 to 10. All right, so ranges here 1 to 10, like 1 to 100, or 1 until 10, which gets all the numbers with the right and non-inclusive, are extremely used in practice, especially for short script-like Scala code. So if you ever wondered how you could apply or print or do something 10 times, you could simply say 1 to 10 dot map, or for each do something. Right? Instead of using recursive function, you could simply do whatever you wanted 10 times. All right. Ranges are a particularly magical data structure that we are going to explore in the advanced Scala course, because there is some really nice magic with these to and until operators on integers, which are not supported by default. So I'll leave that to the advanced stuff. But until then, let's move on to lists. So this is the official signature of the type list. Just as my list is extended by a case object, which is called nil. In our case, it was called empty, and a case class, which we called cons, but in the standard Scala library, it's called : So lists are immutable and extend linear sequence. So because they extend linear sequence, the head, tail, and isEmpty methods are generally fast. They are amortized constant time, but most other operations, like getting an element at a given index, are linear time. Lists are sealed, and they have, like I said, two subtypes: the object nil, which denotes an empty list, and the class : Now, I don't need to remind you that the Scala naming is so permissive. All right, so you've seen lists in practice by calling the apply method from the companion object, but what I didn't show you was how to prepend or append values to it. Let's call this prepended, and let's say I prepend the value 42 to a list. This is how you do it with the : operator. This is syntactic sugar for : dot apply 42 and a list. So if you print this out, prepended, we're going to see 42 and 123. Right? Another operator that is often used in practice is plus : Plus : is also an infix operator between 42 and a list, and it does prepending. If you want to do appending, you get the symmetrical : plus operator. Let's say 89. And if I right click this and run, I get 42, 123, and 89. So this is for append, and this is for prepend. Now, if you want to remember them, you just need to know that the colon is always on the side of the list. Now, there are a number of other things that I didn't really show you. So say, for example, I want a list of 5 elements with the same value. Let's say 5 apples, or apples 5, is list dot, and here's what I write: fill with parameter 5, and then with another parameter list, the parameter apple. So fill is a curried function that takes in a number and a value and constructs a list with 5 times or n times that value. So if I print line this, apples 5, I should see a list of 5 apples. Okay? I also want to show you the makeString method, which is pretty handy when you want to print something very quickly. So if I print line, let's say apples 5, well, let's say a sequence, a list. I want to print a list.makeString, and I want to put a dash between them. MakeString actually concatenates all the values and puts in this guy, or whatever I want to put it. Let's say I want to put dash bar dash in between all the numbers. Then if I print this, I'll print all the elements concatenated with this guy, with this separator in between them. And the rest is history. You already know how to work with lists, so I'm going to move now to arrays. So, still in the context of sequences, we have arrays, which are the equivalent of simple Java arrays. These can be constructed with predefined lengths. So if I say new array of 3 elements, then that will allocate enough memory for 3 elements without actually needing me to give values to those 3 elements. Arrays can be mutated, that is, they are mutable, and they are completely interoperable with Java's native arrays. Indexing is fast in that you can access any element at any position in constant time. But we said that array is a sequence, but where the hell is the sequence in the definition of the array? Let's see that in practice. Alright, back in the IDE, let's construct an array. Say numbers equals array with, say, 1, 2, 3, 4. Right? This is an array. If we wanted to create an array of a given dimension, we can say val 3 elements is array of dim with the type int, and we can put in a number here. And that allocates space for 3 elements without needing me to actually supply values for those 3 elements. So let's actually try to print what, actually call this tree elements. Let's actually name this correctly. So let's try to print 3 elements to see what happens. So prints this very obscure string representation. But if I try to do instead 3 elements dot for each print line, I'm in for a surprise. Because the values are initialized with some default values. So they're not null, they have default values. If I change this to be a string or some other kind of reference type, let's try to see what happens. We have nulls. So for primitive types like int and doubles and booleans, we have default values of 0 or false. But for reference types like string or persons or something else, the values are initialized with null. Now, like I said, arrays can be mutated in place. So if, for example, let's call this mutation. If I say numbers, and watch what I write, numbers2 equals 0, then this will update the value at index 2 with the value 0. So let's print the numbers now. So if I print line numbers dot make string, and let's put in a space as a separator, I should be seeing 1, 2, 0, 4. So instead of 3, I put in a 0. Now, why does this syntax work? Well, this guy is a special syntax sugar for numbers dot update to 0. So the update method is also special in Scala. It's quite rarely used in practice, and it's only used for mutable collections, but this is a syntax sugar that's very similar to apply. So update is also a special method in Scala, and it allows for this kind of syntactic sugar. Now, let's make the connection between arrays and sequences. So if I define numbers sequence, which is a sequence of int, explicitly described here, and on the right hand side I put in numbers. Although numbers is an array which is totally unrelated to the type sequence, again, numbers is an array which is a direct mapping over Java's native arrays, so it has nothing to do with sequences. Despite this, the conversion can be applied, and if I print line number sequence, I should be seeing wrapped array. So this is a special kind of sequence which wraps over an array. So this equal sign is called an implicit conversion. Implicit conversions are a very advanced topic, and we're going to talk about that obviously in the advanced Scala course. It's a really deep rabbit hole, but I just want you to know that there are such things as implicit conversions. So you can convert an array to a sequence via an implicit conversion. The compiler does a lot of magic behind the scenes, and we'll explain how that works in the advanced course. This is how arrays actually have access to sequence methods like makeString. If you pay very, very close attention, numbers here and makeString are underlined, which is a signal from the IDE that implicit conversions happen behind the scenes. Next thing that I want to talk about is vectors. Now, vector is basically in its own world, and it's the default implementation for immutable sequences because it's very efficient. It offers effectively constant time for read and write. It's a very slow-growing logarithmic. It offers fast element addition for append and prepend, and it's implemented as a fixed branch trie with a branch factor of 32. So it holds 32 elements at any one level. That is for memory and cache optimizations. It also offers good performance for very large sizes. So we're actually going to see some examples of using vectors in practice here, and we'll also do a small perf test versus a simple list. So vectors can be computed like saying vector, which is a vector of int, and equals vector 1, 2, 3. Just like you would with any other collection. So if you print this out, you'll see the vector, right? So vector 1, 2, 3. Vectors offer the same functionality as other collections, so I'm not going to bore you too much with them. So let's go to the perf test with vectors versus lists. So here's what I'm going to do. I'm going to write a small method called getWriteTime. I'm interested in getting the average write time for a collection. So I'm going to pass in a collection, which is a sequence of int. This will return a double. We want to measure it in time. And the implementation is going to be the following. I am going to create a new random number generator. New, and the random number generator in Scala is random. Now, I'm going to attempt to write something to a list or to a vector or to this collection a number of times, and then sum up the times required and then divide them by the number of runs. All right, so let's define a number of runs. Let's call this max runs. Let's just say we want 1,000 runs or something like that. All right, so like I said before with ranges, we want to do something for 1,000 times. So how do we do that? Well, we write a small value called times, and let's say we do a for comprehension, and for every iteration, which goes from 1 to max runs, then we yield the following expression. First, we need to get the current time of the system. So current time equals, let's say, system.nanotime. Then I want to do the operation. And then I want to return system.nanotime, which is a different time now, minus current time. So the operation here will take this much nanoseconds. Now the operation here is going to be collection dot, and there is a method called updated, and we need to pass in an index, which is going to be randomly generated, and we're going to pass in a value here, let's say 0. So at the random index, which is r.next int, and the limit here is going to be limited by a capacity. Let's call this max capacity up top. Let's call this like 1,000,000 elements or something like that. So collection updated at a random index from 0 to max capacity. And at that random index, we're just going to put in a value 0 in this collection. And at the end, we're going to measure the time, and we're going to return the time difference between this moment in time at the beginning and the moment in time after the collection updated call was completed. All right, so this is the times. This is a collection of all the measurements of this function. All right, then we need to return the average time, which is basically times.sum, because times is a collection of numbers. And then we'll just multiply this by 1.0, and we'll divide this by max runs. So this is the average time it takes for this collection to be updated at a random index with a random value. The value itself is not that important. So I hope this little benchmark here makes sense. So again, we're instantiating a new random number generator, and for 1 to max run, so basically for 1,000 times, we mark the current time, we try to update the collection, add a random index with a random value. We can actually call our next int. We don't really care. And then we measure the time after the collection.updated was completed, and then we return the time difference. So for 1,000 times, we measure this time, and we return the average. The average is times.sum over max runs. All right, so let's create a list and a vector just to prove how efficient a vector is. So let's call this numbers list, which is say 1 to max capacity. So this is a range, and then I convert that to a list. And a numbers vector, which is 1 to max capacity dot to vector. Okay, so I've instantiated 2 collections here. One is a list and one is a vector. So let's print the test, which is get right time for a numbers list, and get right time for a numbers vector, and try to see what happens. So before we do that, let's get back to the advantages of each collection. So list has the property that it saves the reference to the tail. So if it tries to update the first element, then the list is incredibly efficient. But if you try to update an element in the middle of the list, it's probably not going to be so efficient. Whereas a vector needs to traverse the whole 32 branch tree and then replace that entire chunk. So the advantage of list is that it keeps reference to tails. And the advantage of vector is that the depth of the tree is small. The disadvantage of list is that updating an element in the middle takes a long time. Whereas the disadvantage of vector is that it needs to replace an entire 32 element chunk. We'll see that this is not so much of a disadvantage. All right, so with that in place, let's right click and run this. I have a Core i7 processor and 16 gigs of RAM. This should take a few seconds to run. So the program is running, and here we have some results. So quite a big of a difference. So for the first number, which is for numbers list, we have the average time it takes to write something to a random index in the list and return a new list is almost 9 million nanoseconds, or roughly 9 milliseconds. For a vector, we only have 4,000 nanoseconds, or 4 microseconds. So there's 3 orders of magnitude difference, and that is for a million elements. If we increase the size, the difference is even going to be bigger. So no wonder vector is the default implementation of sequence. Alright, so you've seen some collections in practice. Join me in the next video where we will talk about more.